Hi students, in this video we are going to find the relation between image distance, object distance, refractive index and radius of curvature when a ray of light passes from a rarer medium to a denser medium which is separated by a convex spherical surface. Okay. Now, to derive this derivation or to obtain the relation, we have to make certain assumptions. Three main assumptions are made, and the first one is the object taken is a point object. We are considering a very small object, and the object is placed on the principal axis of the spherical surface. That is the first assumption. Second assumption is the aperture of the spherical surface. You know what is the aperture, isn't it? Aperture means the diameter of the spherical surface is considered to be very small. And the third and the most important assumption made is the angle made by the incident ray and the refracted ray with the principal axis is very small, so that sine and tangent of the angles may be taken as equal to the angle themselves. Now this, if you want, you have studied the binomial expansion of sine theta, cos theta, tan theta, etc. in the, I think in the previous year. You know, sine theta you can written as theta minus theta cube by 3 factorial plus theta raised to 5 by 5 factorial, etc. Now if the angle theta is very small, then we can take only the first term and neglect the remaining terms. So sine theta is approximated to theta if the angle theta is very small value. Same for tan theta. If the angle theta is very small, then tan theta can also be approximated to theta. So using these three assumptions, we are going to derive the relation. Okay. So imagine you have a convex spherical surface which separates a rarer medium of refractive index mu1 from a denser medium having refractive index mu2. Now P is the pole or center of the spherical surface, and this is the principal axis. Okay. Now an object O is placed in the rarer medium on the principal axis. So what happens? A ray of light from the object travels and incidents on the spherical surface, and this surface, since it separates two different medium, a rarer medium and denser medium, it undergoes refraction, and after refraction the image of the object, the real image of the object is performed at point I. We are going to find out what is the, we are going to measure the angle of incidence and angle of refraction. Now one thing you have to remember is any line which is drawn from the spherical surface to the normal, so to the center of curvature, will be always a normal. Any line drawn from the spherical surface to the center of curvature is always a normal. So if this is the center of curvature of the spherical surface, then this is the normal, and this point we can take it as N. The ray meets the spherical surface at point N. Now this is the angle of incidence. Angle between the normal and the incident ray is the angle of incidence, and angle between the refracted ray and the normal is angle of refraction. And I am going to take this as angle alpha, this angle is beta, and this angle is gamma. Next, I am going to draw a line normal from point N to the principal axis, and that normal meets the principal axis at point M. Now why we are drawing this normal is to construct right triangles to use the trigonometric relationship. I hope this diagram is clear to you. Once more I will explain. There is a spherical surface A, B, and P is the pole or center of the spherical surface. Now an object O is placed on the rarer medium on the principal axis of the spherical surface, and the ray of light from the object meets the spherical surface at point N, from where it gets refracted and the image is formed at point I. Okay. Now to draw the normal, a line is drawn from the spherical surface, a line is drawn to the center of curvature which acts at the normal. So this is the angle of incidence, this is the angle of refraction, this angle I am taking as alpha, this angle is beta, and this angle is gamma. Again, a line is drawn from, a normal line is drawn from point N to the principal axis. It meets the principal axis at point M. Now, using this diagram, we are going to derive the relationship. Okay. Now, applying Snell's law. Snell's law to the ray ON, we get sin I by sin R, angle of incidence sin R is equal to refractive index of second medium to refractive index of first medium. This can be written as mu2 by mu1. Also, I told you we are taking the angle so small such the way that sine angles can be approximated to the angle itself, which means this is approximately equal to I by R, or we can write I into mu1, cross multiplying, we get I into mu1 is equal to R into mu2. This is the first equation. So next we are going to find out what is sine I, what is the value of I and what is the value of angle R. For that we take two triangles. First triangle is triangle NOC. You know, the triangle exterior angle is equal to sum of opposite interior angle. So from triangle NOC we get exterior angle I is equal to sum of opposite angle interior angle, that is alpha plus gamma. Equation 2. Similarly, from triangle NIC, exterior angle gamma is equal to R plus beta. So from triangle NIC, gamma is equal to R plus beta. But our aim is to find out what is angle of incidence and angle of refraction. So I am going to rearrange this equation and write R is equal to gamma minus beta. This is equation 2. Sorry, equation 3. Okay. So we got I in terms of alpha, I and R in terms of alpha, beta and gamma. Next we are going to find out what is alpha, beta and gamma. Okay. Okay. For that we are going to use the right triangles. From the right triangle NOM, this triangle, from triangle NOM, tan alpha is equal to, what is tan theta? It is opposite side by adjacent side. So we can write NM divided by OM. Similarly, from triangle NIM, this triangle NIM, we can write tan beta is equal to NM divided by MI. Similarly, from triangle NCM, we are going to find what is tan gamma. So triangle NCM, tan gamma is equal to what? NM divided by adjacent side, that is CM. Okay. Now two approximations are made here. First one I told you, since the angle is very small, tan alpha or tan theta or sin theta can be approximated to theta. Similarly here, tan alpha can be approximated to alpha, tan beta can be approximated to beta and tan gamma can be approximated to gamma. That is the first approximation which we make here. Now the second assumption or approximation which we make is the point M is actually very close to point P. Very close means approximately very near to point P. So we are going to take, instead of point M, we are going to take it as point P. Why we are doing this? Because we know all the measurements, all the distance are measured from the pole, isn't it? So to take the measurements in terms of u, v and all, measure in terms of u, v and all, we are going to assume that the point P is very close to point M. So we can write alpha is equal to NP by OP, beta is equal to NP by PI, and gamma is equal to NP by PC. Now we are going to substitute. Our next step is we are going to substitute the value of alpha, beta and gamma into the equation of I and R. Now we got the equation of I and R as I is equal to alpha plus gamma, so which is equal to NP is common everywhere, so I am taking it outside, NP into 1 by OP plus 1 by PC. Similarly, R is equal to gamma minus beta is equal to NP into 1 divided by PC minus 1 divided by PI. And we are going to substitute the value of I and R in the first equation. And what was the first equation? First equation was mu1 into I is equal to mu2 into R. So mu1 into I, what is I? mu1 into NP into 1 divided by OP plus 1 by PC is equal to mu2 into R. Mu2 into what is R? NP into 1 divided by PC minus 1 divided by PI. Now NP and NP is common, we take it out, cancel it, so we get mu2 into 1 by OP plus 1 by PC is equal to, sorry, mu1 into 1 by OP plus 1 by PC is equal to mu2 into 1 by PC minus 1 by PI. So now we got the equation, all the terms in terms of P, so we can measure and write P, OP, PC, PI, etc. in terms of image distance, object distance and radius of curvature. Now if we look into this diagram, we can see OP is U, but according to the sign convention we are measuring from P. I told all the measurements are taken from P, so we will be measuring in the direction opposite to the ray of light. So OP is equal to minus U. Similarly, PI is the image distance. So PI is equal to V, and PC is the radius of curvature. So PC can be written as R. Now substituting the value of OP, PI and PC in the above equation, we get, substituting the value of OP equal to minus U, PI is equal to V and PC is equal to R in the above equation, we get mu1 into 1 by minus U plus 1 by R is equal to mu2 into 1 by R minus 1 by V. Now I am going to rearrange this equation where I can bring the R terms, 1 by R terms together. So I get mu2 minus mu1 divided by R is equal to mu2 by V minus mu1 by U. I am going to bring this term to the side and this term I am bringing this side. So we get the final equation as mu2 minus mu1 by R is equal to mu2 by V minus mu1 by R. This is the equation for the refraction through a convex spherical surface, which relates the image distance, object distance, radius of curvature and the refractive index. Now one special condition is there. If suppose the first medium, that is a rarer medium, is air, then the value of refractive index for air is 1. So mu1 is equal to 1 and we can write mu2 as mu. So the above equation can be written as mu minus 1 by r is equal to mu by v minus 1 by u. This is a special condition if the rarer medium is air. I hope this derivation is clear to you. I will explain to you one more time the steps. First what we did is we applied the Snell's law and we got I mu 1 is equal to R mu 2. Then we using angles alpha, beta and gamma, we found out what is I and R. Then we found out what is alpha, beta and gamma, substituted in the main equation, applied the sign convention, applied the values of OP, PI, etc. We arranged the equation and we got the final equation as mu 2 minus mu 1 by R is equal to mu 2 by V minus mu 1 by U. I hope this derivation is clear to you. Thank you.